All right, today we're going to talk about the single most important invention of the modern era. Seriously, it's this tiny, unsung hero that makes literally everything in your life work, from your phone to your car to your coffee maker. So take a second and think, what is it? You might guess the internet, maybe the microchip. Well, you're close, but it's actually the thing that makes all of those things possible, and it's hiding in plain sight by the billions and billions. It is the transistor, and at its core, it's really just a switch. That's it. But it's a switch with no moving parts, one that can be flipped on and off billions of times a second, and it's so incredibly small you can cram billions of them onto the tip of your finger. It's the fundamental atom of our entire digital world. So how does this little magic switch actually work? Well, it turns out there are a couple of major families of them. So first up, let's meet the pioneers, the OGs of the transistor world, the bipolar junction transistors, or what everybody calls BJTs. Now, why the name bipolar? It sounds super technical, right? But it's not. It just means it uses two types of electrical charge to get the job done. You've got the negative electrons, which we all know and love, and their positive counterparts, which are called holes. Two poles, bipolar. Simple as that. So inside this bipolar family, you've basically got two main siblings, the NPN and the PNP. The easiest way to picture them is like a simple little sandwich of silicon. One has a slice of P-type material squeezed between two N-types, and the other one is just the exact opposite. And that simple layered structure, well, that's the key to everything. Okay, so how does this BJT switch actually turn on and off? The best analogy, honestly, is a water valve. Imagine you send just a tiny trickle of current into that middle layer of the sandwich, the paste. That little trickle acts like your hand turning the valve's handle. It opens up a gate and whoosh! A huge rush of current is allowed to flow through the other two layers. A tiny input controls a massive output. And this right here, this is the secret sauce. The control current is way smaller than the main current it's controlling. This ability to amplify a tiny little signal into a huge one is what makes these things so unbelievably powerful. But wait, that's not the only way to build one of these switches. Enter the second major family, the field effect transistors, or FETs. And they come at the problem from a completely different angle. The name literally gives the secret away. Instead of using a small current to open the gate like a BJT does, a FET uses an invisible electric field. It's like having a little force field that squeezes or opens a channel for electricity to flow through. No touching required. And just like the BJT family, FETs have their own members. A really common type is the JFET. And surprise, surprise, it also comes in two main flavors, N-channel and P-channel. You can always tell them apart just by looking at which way the little arrow is pointing in their circuit diagram. Okay, this is a total game changer. In a FET, the control inputs, they call it the gate, is completely isolated from the main path where the current is flowing. The best way to think about it is like squeezing a garden hose to stop the water. Your hand controls the flow, right? But none of the water from your hand actually mixes with the water in the hose. It's the exact same idea here, which means the control signal uses almost no current at all. It's basically zero. All right, so we've got our two contenders in the ring, the BJT, which is controlled by current, and the FET, which is controlled by a voltage field. Let's put them head to head and really see what the crucial differences are. Okay, little pop quiz. We already know the BJT is called bipolar because it uses those two types of charge carriers, right? The electrons and the holes. So, with what we know now, what does that make the FET? It's a unipolar device, uni as in one. A FET only needs one type of charge carrier to work. Either it's using electrons or it's using holes, but it never uses both at the same time. And that is a huge difference in how they work on a physical level. Now, this difference leads to one of the biggest practical advantages. Because that FET gate is isolated, it has this incredibly high input resistance. The technical term is impedance. Basically, it fights really hard against letting any control current in. The BJT, on the other hand, needs that current, so its input impedance is much lower. And this is why FET are way more efficient for a ton of modern jobs. So let's just lay it all out, side by side, because this is the whole shebang right here. BJTs are current-controlled, they're bipolar, and they need a little sip of input current. FETs, on the other hand, are voltage-controlled, unipolar, and need virtually zero input current. Two totally brilliant but different solutions to the exact same problem. Okay, so if we have these two amazing families, which one actually runs our world today? I mean, which one is in the device you're watching this on right now? Well, the answer lies with a very special member of that FET family. And the undisputed champion is the MOSFET. It's a specific kind of FET that has properties that just make it absolutely perfect for manufacturing at an insane scale. We're talking billions at a time. The CPU in your computer, the memory in your phone, they are just packed to the gills with these tiny MOSFETs. So here's the bottom line. It's the principles of that field effect family, controlling electricity with a voltage field instead of a current, that ultimately unlocked the entire digital revolution. This one tiny, hyper-efficient, voltage-controlled switch is the brick that built our modern world. It's pretty incredible when you think about it. We've gone from these early, clunky devices to fitting billions of transistors on a single chip. For decades, the game plan was simple. Just make them smaller, and things get faster. But we are now slamming right up against the physical limits of how small you can make something out of silicon. So the huge trillion-dollar question for the next generation of technology is, what comes next?